They held together, spinning in defiance of every gravitational model we trusted. This puzzle laid the groundwork for the concept of dark matter, a mysterious form of matter that doesn't emit light, but adds mass, and therefore gravitational pull to galaxies. Enter Vera Rubin, a pioneering astronomer in the 1970s, who provided some of the most compelling evidence for dark matter through her study of spiral galaxies. Rubin and her colleague Kent Ford measured the rotation curves of galaxies like Andromeda and found that the speeds of stars remained constant far beyond where the luminous matter ended. Her research confirmed that there must be a vast halo of invisible mass, dark matter, extending far beyond the glowing disks of stars. Rubin's work was revolutionary. She didn't just suggest that dark matter might exist. She showed that it was essential for the stability of galaxies. Still, dark matter remains elusive. We know it's there, but we don't know what it's made of. It doesn't interact with light, meaning it cannot be seen. It doesn't appear to interact much with ordinary matter either, except gravitationally. For decades, scientists have been hunting for the fundamental particle or substance that makes up dark matter. Hypothetical entities like WIMPs weakly interacting massive particles, actions, or sterile neutrinos. Deep underground labs shielded from cosmic rays have been constructed to detect even the faintest collision between a dark matter particle and ordinary atoms, but so far, none have been conclusively found. The search continues. Meanwhile, a second, even greater mystery began to emerge in the late 20th century, this one not about the structure of the universe, but its expansion. In 1929, Edwin Hubble had discovered that the universe was expanding, with galaxies moving away from one another at speeds proportional to their distance. For decades, it was assumed that this expansion must be slowing down over time due to the pull of gravity. After all, if you toss a ball into the air, gravity slows it down, even if you throw it very fast. So too, it was thought, the universe must eventually stop, or even reverse its expansion in a big crunch. But in 1998, two independent teams of astronomers, using distant Type Ia supernovae as cosmic yardsticks, found something astonishing. The expansion of the universe was not slowing down, it was speeding up. These ancient exploding stars appeared dimmer than expected, suggesting they were farther away than they should have been. This meant that the universe had been expanding more rapidly in recent times than in the past. Something was pushing it apart. To explain this cosmic acceleration, scientists proposed the existence of a repulsive force permeating space, what we now call dark energy. Unlike dark matter, which pulls things together, dark energy pushes them apart. It behaves as if empty space itself had a kind of built-in energy, something that grows stronger as the universe expands. This idea was eerily similar to something Einstein had once proposed, the cosmological constant, a term he originally inserted into his equations to keep the universe static. He called it his greatest mistake, but today the cosmological constant, or something like it, may be very real. and it might be responsible for the fate of everything. Where dark matter holds the universe together, dark energy tears it apart. Together, they dominate the cosmic balance, and yet we cannot see or directly measure either of them. They are inferred through their gravitational footprints, their subtle warps in space and time. The closest analogy might be seeing ripples on the surface of a pond and deducing that something, perhaps a stone or a breeze, has disturbed it, even if the cause itself is invisible. In this sense, dark matter and dark energy are the ripples of the unknown. The true proportions of the universe are mind-blowing. Of all the matter and energy in existence, ordinary matter, the stuff we can see, touch, and build telescopes with, accounts for just 4.9%. Dark matter makes up around 26.8%. Dark energy dominates with a staggering 68.3%. This cosmic recipe tells us that everything we've ever known, every planet, every galaxy, every supernova, is just a tiny fragment of reality. It's as if we've been staring at a painting, marveling at its colors, only to discover that it's just a corner of a vast mural, most of which is covered by a black veil. The discovery of dark matter and dark energy fundamentally changed our understanding of cosmology. Before, we thought we were closing in on a theory of everything, a neat and tidy equation that could explain the universe from beginning to end. Now we realize we may be at the very beginning of our understanding. The universe is not just stranger than we imagined, it's stranger than we can imagine. And yet, our tools and our curiosity push us forward. The cosmic microwave background, the oldest light in the universe, has provided us with a baby picture of the cosmos, just 380,000 years after the Big Bang. Detailed measurements from missions like WMAP and Planck show tiny fluctuations in this ancient light, clues about how matter first clumped together and how dark energy began its slow, silent work. These patterns help us map the evolution of the universe and refine our models of dark matter and dark energy. But for every answer, more questions arise. Is dark energy constant, or does it change over time? Is dark matter a single type of particle or a complex mix? Could both be manifestations of an even deeper phenomenon, something we have no name for yet? The search continues, not just in observatories and laboratories, but in the imagination of scientists. Some have even proposed that our entire universe might be just one bubble in a vast multiverse, each with its own balance of matter and energy. In such a scenario, dark energy might differ from one universe to another, and we just happen to live in a universe where it permits the formation of stars, galaxies, and life. Others suggest that our theories of gravity might be incomplete. Perhaps we don't need to add dark matter and dark energy to our equations. Perhaps the equations themselves need to change. These modified gravity theories, like MOND modified Newtonian dynamics and emergent gravity, try to explain cosmic behavior without invoking unseen substances. But so far, none have explained the observations, as well as the dark matter/dark energy model. In many ways, dark matter and dark energy are placeholders, names we've given to effects we don't yet understand. They are signposts at the edge of human knowledge, like ancient maps that marked the unknown with the words, "Here be dragons." Our cosmic map is surrounded by regions labeled dark matter and dark energy. But we are not afraid. We are explorers. And where there is mystery, there is discovery waiting. This is the dark side of the universe, not empty or lifeless, but full of hidden forces, unseen structures, and boundless questions. It is a realm where light cannot guide us, where equations falter, and where every step forward feels like a leap into the void. But it is also the frontier of science, the place where our understanding will either shatter or evolve. And that is why we must go there. The universe, to the naked eye, seems like a boundless sea of isolated lights, stars twinkling against a backdrop of darkness, scattered randomly across the sky. But zoom out far enough, and a different pattern begins to emerge. Galaxies are not sprinkled randomly. They cluster, stretch, form strands, and leave vast empty regions between them. It is as if the cosmos itself is woven from invisible threads, a kind of cosmic lattice holding everything in place. This is the cosmic web, and at the heart of this structure lies a force we cannot see, dark matter. The term dark matter was first coined in the 1930s by Swiss astrophysicist Fritz Zwicky, who observed that galaxies in the Coma cluster were moving too quickly to be held together by the visible matter alone. Using a method called the virial theorem, Zwicky compared the kinetic energy of the galaxies from their motion to the gravitational potential energy implied by their visible mass. The numbers didn't add up. There had to be more mass, a lot more than what could be seen. He proposed the existence of dunkel materie, dark matter. But at the time, his findings were largely ignored, considered speculative or erroneous. It would take several decades and much more evidence before the scientific community began to accept his revolutionary idea. The evidence began to accumulate steadily, and one of the strongest cases came from the groundbreaking work of Vera Rubin in the 1970s. She studied the rotational velocities of stars in spiral galaxies, expecting to find that stars farther from the galactic center would move more slowly, just as planets farther from the sun orbit more slowly due to weaker gravitational pull. But Rubin found the opposite. Stars in the outer regions of galaxies move just as fast as those near the center. This defied Newtonian physics. If only the visible mass, stars and gas, were present, these galaxies should have flung themselves apart. But they didn't. Something invisible was holding them together. That something became dark matter. Unlike ordinary matter, dark matter doesn't interact with electromagnetic radiation. It doesn't emit, reflect, or absorb light. That's why it's dark. But what it does interact with is gravity. It exerts a gravitational pull, and this is how we detect its presence, not by seeing it, but by seeing its effects. Over time, astronomers realized that this unseen mass wasn't just a feature of galaxies, it was a universal phenomenon. Every spiral galaxy studied showed the same kind of flat rotation curve. Galaxy clusters moved and formed under gravitational influences far greater than visible matter could explain. The gravitational footprints of dark matter were everywhere. But dark matter's role extends far beyond galaxy dynamics. It is also responsible for the formation of structure in the universe, from stars and galaxies to massive clusters and superclusters. After the Big Bang, the universe was hot, dense, and relatively uniform, with only tiny quantum fluctuations in density. These fluctuations were captured in the cosmic microwave background CMB, the afterglow of the Big Bang, and studied in detail by missions like WMAP and Planck. But those slight differences in density wouldn't have been enough for ordinary matter, which interacts with radiation, to clump together into galaxies. Something else, something invisible and non-interacting, must have formed the first gravitational wells. That something was dark matter, because dark matter doesn't interact with light or radiation. It was able to start clumping together very early in the universe's history. particles, theoretical particles that interact via the weak nuclear force and gravity, but not electromagnetism. These particles, if they exist, would be abundant and massive enough to explain the observed gravitational effect. But decades of searching using underground detectors, space telescopes, and particle accelerators have yet to confirm their existence. Other candidates include actions, extremely light and elusive particles originally proposed to solve problems in quantum chromodynamics. Actions could be produced in huge numbers in the early universe and may form a kind of invisible field pervading space. Still others suggest sterile neutrinos, hypothetical relatives of the known neutrinos, which might interact only via gravity. There are even ideas of dark matter being composed of primordial black holes formed shortly after the Big Bang, not from stars, but from collapsing regions of high density. Yet none of these theories have been confirmed. Every attempt to detect dark matter particles, be it with the Lux-Zeppelin experiment, XENON-1T, or the Large Hadron Collider, has come up empty or produced results that could not be conclusively linked to dark matter. This has led some scientists to propose even more radical ideas. Maybe dark matter isn't a particle at all. Maybe our theory of gravity is incomplete. Theories like MOND-modified Newtonian dynamics suggest that the laws of gravity change under extremely weak fields, like those found in galaxies, removing the need for dark matter entirely. Other models propose extra dimensions, or a new fifth force, that we haven't yet detected. These ideas are controversial and often struggle to match the observational evidence, as well as the dark matter model does. But they highlight how little we still know. Despite these challenges, the concept of dark matter remains a cornerstone of modern cosmology. Its fingerprints are everywhere, from the earliest stages of the universe to the structure we see today. We may not yet know what it is, but we know what it does. It holds galaxies together, binds clusters into superclusters, forms the cosmic web, and enables the birth of stars. It is the glue of the cosmos. As we develop more sensitive detectors and more powerful telescopes, we are inching closer to uncovering its true nature. The upcoming Vera C. Rubin Observatory, named, fittingly, after the woman who confirmed dark matter's existence, will survey the entire southern sky every few nights, creating an unprecedented catalog of galaxies, supernovae, and gravitational lenses. Missions like Euclid and the Nancy Grace Roman Space Telescope will map the distribution of dark matter with exquisite precision. With each observation, the picture becomes clearer. But perhaps the most important thing dark matter has taught us is humility. For centuries, humans believed Earth was the center of the universe. Then we learned we orbit the sun, then that the sun is one of billions of stars in the galaxy, and the galaxy one of billions in the cosmos. Now we face a new demotion. Even the matter we're made of is a minority component of the universe. We are made of stardust, yes, but the stars themselves are outnumbered by an invisible sea. And yet, In this darkness, we find wonder, because even though we cannot see dark matter, we can feel its presence in the shape of galaxies, in the flow of time, in the whispers of gravity. We live in a universe stitched together by unseen threads, and every discovery pulls on one of those threads, unraveling the next mystery. Dark matter is not just a puzzle, it is a story, one still being written, one that begins in the earliest moments of time and continues into the distant future. And like all great stories, it demands exploration, imagination, and above all, curiosity. For centuries, gravity was thought to be the master of the universe. From falling apples to orbiting planets, from the collapse of stars to the pull between galaxies, gravity reigned supreme. It was, for all intents and purposes, the invisible hand that shaped everything. Isaac Newton defined it with precise mathematics. Albert Einstein expanded it into a curvature of space-time. The universe, it seemed, danced to gravity's rhythm, but then came a discovery so unexpected, so bewildering, that it shook the very foundation of cosmology. In the late 1990s, two teams of astronomers were working independently on what seemed like a straightforward project, measuring how fast the universe's expansion was slowing down. After all, if the Big Bang launched the cosmos outward, and gravity pulls everything together, then the expansion should be decelerating. It was just a matter of figuring out how fast it was slowing. To do this, the teams used a special kind of exploding star called a Type Ia supernova, a stellar detonation so bright and consistent that it acts as a standard candle. By comparing how bright a supernova appears from Earth with how bright we know it should be, we can calculate how far away it is. When combined with redshift measurements, this gives a snapshot of the expansion rate at different times in the past. The results shocked everyone. Instead of slowing down, the universe was speeding up. These distant supernovae were fainter than expected, not because they were less luminous, but because they were farther away than they should have been. This meant that over time, the expansion of space wasn't decelerating, it was accelerating. Something was acting against gravity, something powerful enough to push galaxies apart faster and faster as time went on. The discovery was so revolutionary that it earned the 2011 Nobel Prize in Physics for the leaders of both teams, Saul Perlmutter, Brian Schmidt, and Adam Rees. But even with the recognition, a vast question remained. What is this mysterious force pushing the universe apart? Scientists called it dark energy. Like dark matter, it was invisible. But unlike dark matter, which clumps together and pulls things in, dark energy was repulsive. It seemed to be embedded in the fabric of space itself, and as space grew, the influence of dark energy grew with it. But what is dark energy? There are several theories, and none are conclusive. The simplest explanation, and the one most widely accepted for now, is something known as the cosmological constant, a term that Einstein originally introduced into his equations of general relativity in 1917. At the time, he thought the universe was static, and to make his equations fit, he added a fudge factor that counteracted gravity on large scales. Later, after Hubble discovered that the universe was expanding, Einstein called the cosmological constant his greatest blunder. And yet, nearly a century later, that same term has returned as the leading explanation for dark energy. In this model, empty space is not really empty. Instead, it's filled with a kind of energy, a vacuum energy, that exerts negative pressure and causes space to expand. It's a bizarre idea that nothingness has weight, and that the more nothing you have, the more it pushes everything apart. But while the cosmological constant fits the data well, it comes with a huge problem: its value. Quantum field theory predicts that the vacuum energy of empty space should be staggeringly large, about 10 power 120 times higher than what we observe. That's a 1 followed by 120 zeros. This discrepancy is the most significant known mismatch between theory and observation in physics. It's not just a rounding error. It's a cosmic scream that something doesn't add up. To solve this, some physicists have proposed that dark energy isn't constant at all. Instead, it might be a dynamic field that evolves over time, much like the Higgs field that gives particles their mass. This idea is called quintessence, after the fifth element of ancient philosophy. Unlike the cosmological constant, quintessence could change with the expansion of the universe, perhaps explaining why dark energy became dominant only relatively recently in cosmic history. Others suggest that dark energy might be tied to extra dimensions. According to string theory, the universe may have more than 4 dimensions, with the others curled up at microscopic scales. Dark energy could be a gravitational leakage into these hidden dimensions, or a side effect of forces we don't yet understand. Still more radical are the ideas that the laws of gravity themselves may need revision. Perhaps general relativity breaks down on cosmic scales, and what we see as acceleration is actually a flaw in our model. Modified gravity theories like FR gravity, brain world models, or emergent gravity attempt to account for cosmic acceleration without invoking dark energy. But as of now, these remain speculative, and none fit the data as cleanly as the dark energy model. So far, all attempts to detect dark energy directly have failed. We see its influence on the cosmos, on the large-scale structure, on the growth of galaxy clusters, and on the ancient light of the CMB, but we don't know what it's made of, or whether it even is a substance. It's as if we're seeing the universe being pulled by invisible strings, but we have no idea who's holding the other end. And yet, its impact is profound. Dark energy makes up roughly 68% of the total energy content of the universe. That means the majority of what exists is not matter, dark, or otherwise, but this repulsive, accelerating energy. It dominates the fate of the cosmos. If dark energy remains constant, the universe will continue to expand forever, growing colder and emptier as galaxies drift apart, stars burn out, and black holes evaporate. Eventually, all structure will vanish beyond the cosmic horizon. This is known as the heat death of the universe, a slow, quiet fading into darkness. But if dark energy grows stronger over time, it could lead to a far more dramatic end, the Big Rip. In this scenario, the repulsive force would increase so much that it tears apart galaxies, stars, planets, and even atoms themselves. The fabric of space would literally rip itself apart. Alternatively, if dark energy is temporary, if it weakens or reverses, gravity could regain dominance, halting the expansion and causing the universe to collapse in a big crunch. There's even a possibility of a cyclic universe, oscillating between expansion and collapse. Right now, we don't know which future awaits us, but one thing is clear. The ultimate fate of the universe depends on the nature of dark energy, and that makes studying it one of the most important missions in modern cosmology. Upcoming space telescopes are being designed specifically to study dark energy. The Euclid mission, launched by the European Space Agency, will map billions of galaxies to measure how dark energy has influenced cosmic expansion over time. The Nancy Grace Roman Space Telescope, NASA's answer to the dark energy question, will use wide-field infrared imaging to track the growth of structure in the universe and provide high-precision measurements of supernova distances and redshifts. complexities of galaxy formation. They allow scientists to study how cosmic expansion works without interference from messy astrophysical processes. Some researchers believe that voids may even help us detect deviations from general relativity or uncover new physics related to dark energy. Their quietness makes them cosmic control groups in an experiment on the nature of reality. Cold spots in the CMB, the universe's birthmarks. When we peer into the depths of the cosmos using radio waves tuned to microwave frequencies, we see something remarkable, a faint glow that fills the entire sky. This is the cosmic microwave background, the afterglow of the Big Bang, emitted just 380,000 years after the universe began. It's the oldest light we can observe, and it carries with it a wealth of information about the early universe. But the CMB isn't perfectly smooth. It's dappled with tiny fluctuations in temperature, mere microkelvins above or below the average of 2.725 K. These tiny ripples are the seeds from which galaxies would later grow. But among them are features far stranger than statistical noise. One such feature is the CMB cold spot, a vast, unusually cold region in the southern hemisphere of the sky. First detected by the Wilkinson Microwave Anisotropy Probe and later confirmed by the Planck satellite, the cold spot is about 1.8 billion light-years across, and its temperature is significantly lower than surrounding regions. What caused it? There are several theories. One possibility is that it's a statistical fluke, a rare but natural low-temperature fluctuation. Another hypothesis suggests it may be a supervoid, an enormous region of space with fewer galaxies, which causes CMB photons to lose energy as they pass through. However, even this may not fully explain the cold spot's properties. More speculative ideas suggest it could be evidence of something even stranger, like a collision between our universe and another bubble universe in a multiverse scenario. While unproven, the cold spot has become a focal point for scientists exploring the boundary between known cosmology and the great unknown. It's a fingerprint left on the baby universe, and we still don't fully know whose hand left it. Hidden galaxies, the zone of avoidance. When astronomers map the universe, they usually look outward in all directions. But there's one region that has always been harder to explore, the area blocked by our own Milky Way galaxy. Our galaxy is a massive spiral disk filled with stars, dust, and gas. When we try to look through it, especially near the galactic center, we're met with dense clouds of material that absorb and scatter light. This creates a blind spot in the cosmic map known as the zone of avoidance. In the past, astronomers simply assumed that not much lay behind this wall of dust. But as technology improved, especially with infrared and radio astronomy, we began to peek behind the curtain. And what we found was astonishing. Hidden behind the Milky Way's thickest dust lanes are entire galaxies, clusters, and superclusters. For example, in 2016, astronomers discovered the Vela supercluster, a massive structure containing thousands of galaxies, hidden completely within the zone of avoidance. It's one of the largest known structures in the nearby universe, and we only just found it by mapping hydrogen gas using the 21 cm radial line and by using infrared telescopes like WISE Wide Field Infrared Survey Explorer. We are now uncovering these ghostly realms. It's as if our own galaxy has been hiding treasures behind a veil, and now the veil is lifting. But this raises an important question. What else is hiding in plain sight? Could some of the largest structures in the universe still be undiscovered, simply because they lie in directions we haven't looked deeply enough? As observational tools improve, we may uncover not just hidden galaxies, but entirely new types of matter or structure. The zone of avoidance may soon become the zone of discovery. Dark galaxies, ghost cities of the cosmos. We often think of galaxies as brilliant cities of stars, billions of suns orbiting around a common center. But what if some galaxies never turned on their lights? This brings us to the eerie concept of dark galaxies. These are hypothetical galaxies composed almost entirely of dark matter and gas. Structure and dynamics similar to ordinary galaxies. Astronomers have long suspected their existence. After all, if dark matter makes up most of the mass in the universe, and if galaxies form within dark matter halos, then surely some halos never lit up. These dark galaxies may have failed to form stars due to environmental conditions, lack of cooling mechanisms, or suppression by nearby radiation. In recent years, observations have begun to uncover candidates for these ghostly structures. One striking example is Dragonfly 44, a galaxy discovered in the Coma Cluster. It has the mass of the Milky Way, but emits only 1% of its light. It's essentially invisible unless you know exactly where to look. Dragonfly 44 is composed of 99.99% dark matter, and it's not alone. Other ultra-diffuse galaxies have since been found, many with anomalously low star counts, despite massive dark matter halos. Some even appear to lack dark matter entirely, creating tension and excitement among astronomers. If dark galaxies are common, they could help solve the missing satellites problem, the discrepancy between the number of dark matter halos predicted by simulations and the number of observable galaxies. It's possible that many dark matter halos never formed luminous galaxies, but still exist, invisible to our eyes. Finding and mapping these ghost cities requires special techniques. Radio astronomy can detect cold hydrogen gas, a signature of potential dark galaxies. Gravitational lensing can reveal their mass indirectly. As technology improves, we may soon uncover a hidden skeleton population of the universe, worlds that never saw the light. The tools that peer into darkness. How do we even explore these invisible places? We need more than just better eyes. We need different eyes. Telescopes like Hubble gave us a glorious window into the visible universe, but the James Webb Space Telescope goes further. With its infrared vision, it sees through dust and into the earliest epochs of cosmic history. It can peer into the zone of avoidance, detect hidden star-forming regions, and even look into the hearts of galaxies where supermassive black holes lurk. On the radio side, instruments like ALMA Optima Large Millimeter/Submillimeter Array and MeerKAT allow us to trace cold gas and dark galaxies across vast distances. Soon, the Square Kilometer Array will be the largest radio telescope ever built, mapping the universe in exquisite detail, even the parts we can't see with light. And on a larger scale, gravitational lensing and weak lensing surveys, like those from the Dark Energy Survey, help us map the invisible mass of the universe. In short, the tools are catching up to the questions, and the invisible places are becoming visible. What do the invisible places teach us? In a universe that seems dominated by stars, it's tempting to focus on the brilliant, but the quiet places, the voids, the shadows, the cold, and the dark are where cosmic truth often hides. Voids teach us about the geometry and expansion of space. Cold spots reveal clues about the earliest seconds after the Big Bang. Hidden galaxies remind us that even nearby space is not fully mapped. Dark galaxies hint at new physics or new behavior of matter under extreme conditions. In every case, the absence of light isn't a flaw in the universe. It's part of its design. As we leave the invisible places behind, we turn now to the methods that make this exploration possible. In the next chapter, we'll look at how astronomers see the unseen, using gravitational distortions, cosmic radiation, and a full spectrum of light invisible to the human eye. The darkness may hide things from our sight, but not from our curiosity. In our everyday lives, sight seems straightforward. Light enters our eyes, reflects off objects, and our brain interprets the image. But in space, this simplicity fades. The cosmos hides most of its contents in darkness, not just dark as in dim, but fundamentally undetectable by traditional means. So, how do we find galaxies made of nothing but gas? How do we study objects that don't emit light? How do we measure the pull of things we can't even touch? To see the invisible universe, astronomers have learned to think like detectives, piecing together clues, distorting reality, and listening to the silent echoes of cosmic events. In this chapter, we explore the powerful tools, methods, and ideas that allow us to study the unseen structure of the universe, everything from dark matter to gas clouds to ancient light from the dawn of time. Gravitational lensing, nature's cosmic telescope. Let's begin with one of the most remarkable phenomena predicted by Einstein's theory of general relativity, gravitational lensing. The idea is deceptively simple. According to Einstein, mass curves space-time. A massive object, like a galaxy or a black hole, bends the space around it. If light from a distant galaxy passes near such a mass, it doesn't travel in a straight line. It curves, just like how light bends when passing through a lens. This bending of light allows astronomers to study invisible mass. If we observe distorted images of distant galaxies, we can deduce that there must be something massive, perhaps a cluster of galaxies or a dark matter halo, warping the light between us and the source. There are two main types of gravitational lensing. One, strong lensing. Strong lensing occurs when the alignment between the observer, the lensing mass, and the background light source is nearly perfect. This can create spectacular effects. Einstein rings, multiple images of the same object, or giant arcs stretched across space. These are not artistic renderings. They're real, cosmic scale optical illusions. One famous example is the Einstein cross, where four images of a distant quasar appear around a foreground galaxy. In clusters like Abel 1689's, dozens of distant galaxies appear as streaks and arcs, magnified and bent by the gravity of the massive cluster in front of them. From these distortions, astronomers can map where the mass is, even if no light comes from it. This is how we discovered that galaxy clusters contain much more mass than their visible stars, and gas can account for, direct evidence of dark matter. 2. Weak lensing. Weak lensing is more subtle. It doesn't produce dramatic arcs, but slight distortions in the shapes of millions of galaxies. By analyzing statistical patterns in these distortions across the sky, astronomers can create mass maps of the universe, showing how dark matter is distributed across cosmic time. Projects like the Dark haircut. In the upcoming Square Kilometer Array, radio astronomy is helping find dark galaxies, map large-scale structure, and even test Einstein's theories on galactic scales. Each wavelength reveals a new facet of the cosmos. Together, they allow us to construct a complete picture of the invisible universe. Particle detectors and underground labs searching for dark matter, while telescopes explore space. Physicists on Earth are building instruments to catch dark matter directly. The most popular dark matter candidates are WIMP's weakly interacting massive particles, hypothetical particles that would rarely interact with ordinary matter, but might occasionally collide with an atomic nucleus, releasing a tiny burst of energy. To detect such rare events, scientists build massive detectors deep underground, shielded from cosmic rays and other noise. Examples include Lux Zeppelin in South Dakota, XENON-1T in Italy's Gran Sasso Lab, Super CDEMS in Canada. These detectors use large vats of liquid xenon or germanium, waiting for a tiny flash of light or a faint heat pulse caused by a WIMP. So far, the results are inconclusive, but tantalizing. If even one particle is detected, it could reveal the identity of dark matter, transforming invisible theory into tangible discovery. Simulations and AI are modeling the unseeable. Sometimes we can't observe directly, so we simulate. Massive computational projects like the Illustris and Millennium simulations create digital universes, evolving them using the laws of physics and assumptions about dark matter, dark energy, and gravity. These simulations generate cosmic web structures, galaxy evolution models, star formation rates. By comparing simulated universes to observations, scientists test hypotheses about invisible processes, like how dark matter clumps or how voids grow. With the rise of AI and machine learning, astronomers can now sift through petabytes of data, spotting patterns humans might miss, detecting lensing signatures, classifying galaxy morphologies, and searching for anomalies that might signal new physics. In the age of big data, visibility isn't just about light, it's about information. Why seeing the invisible matters? Studying the invisible isn't just a technical challenge, it's a philosophical one. We've learned that most of the universe is not made of what we can see. Stars, planets, gas, dust, all of it accounts for less than 5% of the total cosmic pie. The rest is hidden, dark matter holding galaxies together, and dark energy pushing them apart. But even within the visible fraction, so much is obscured by dust, distance, or limitations of our tools. By learning to see differently, to feel gravity, to listen to microwaves, to decode distortion, we expand not just our picture of the universe, but our concept of reality itself. We learn humility, that what is unseen may be more important than what is seen. We learn curiosity, that every void and shadow might hide something beautiful. And we learn that science is not just about answers, but about looking deeper, again and again, until even the invisible becomes known. The concept of the dark side of the universe, the vast realms of dark matter and dark energy, has challenged our understanding of reality. But what if this invisible cosmos is just the surface of a far stranger truth? What if the darkness we observe is a glimpse into a deeper, more complex reality that transcends our own universe? This leads us to some of the most speculative, fascinating, and mind-bending ideas in modern physics. The possibility that our universe is part of a much larger multiverse, connected to realms and dimensions beyond ordinary perception. The idea of a multiverse suggests that what we call the universe might be only one bubble in an immense cosmic sea, containing countless other universes with their own laws of physics, particles, and even dimensions. This is not merely science fiction, but a serious topic of research and debate among cosmologists and theoretical physicists. The multiverse idea has grown out of attempts to reconcile puzzling features of dark matter, dark energy, quantum mechanics, and string theory. One way to imagine this is to think of our universe as a three-dimensional brain floating in a higher dimensional space. According to some versions of string theory and M theory, there may be up to 11 dimensions, most of which are hidden or compactified so tightly we cannot perceive them. Our universe could be one such brain, while other brains exist nearby, but invisible to us. These other universes might have their own dark matter, energies, and even forms of life. Dark matter itself could be a manifestation of matter existing on a parallel brain that interacts with ours only through gravity or other subtle forces. Some models suggest that what we perceive as dark matter is actually shadow matter residing in a hidden sector. This shadow matter would not emit or absorb light, making it perfectly invisible, yet its gravitational pull would affect our universe. If true, this would revolutionize how we think about matter and existence. The enigma of dark energy might also be connected to extra dimensions. The accelerating expansion of the universe could be caused by gravity leaking into higher dimensions, weakening its pull in our brain and allowing space to stretch faster. This is a striking possibility that ties together cosmic acceleration and the fundamental fabric of reality. Another theoretical framework, called the landscape of string theory, suggests that there are an enormous number, on the order of 10 circumflex 500, of possible vacuum states, each corresponding to a different universe with its own physical constants and laws. Our universe's particular values of these constants, which appear finely tuned for the emergence of life, might be just one selection among countless others. In this view, dark energy's observed value could be explained anthropically. We live in a universe where conditions are just right, because otherwise, we wouldn't be here to observe it. This leads to philosophical questions, as well as scientific ones. If countless universes exist, each with different realities, what does that mean for our sense of uniqueness? Are we just one tiny island in a vast cosmic archipelago? And how could we ever test or prove the existence of these other universes, if by definition they lie beyond our observable horizon? Some scientists have proposed that indirect evidence of other universes could appear in subtle patterns in the cosmic microwave background radiation or through gravitational wave signals resulting from collisions between brains. However, these remain highly speculative and controversial. Beyond multiverses and brains, some physicists have suggested the possibility of hidden forces and particles interacting with dark matter. These hidden sectors might have their own rich physics, possibly even dark photons or mirror matter that mirror the particles in our familiar universe, but interact weakly or not at all with ordinary matter. If detected, such discoveries would dramatically expand our understanding of reality. All these theories underline a humbling truth. The universe we know, the one visible in stars and galaxies, is likely just a small slice of a far grander and stranger cosmos. The dark side, with its invisible matter and energy, might be our window into this hidden multiverse. Yet, this exploration pushes the boundaries of what science can currently test. As physicist David Deutsch said, understanding the multiverse requires a new kind of scientific imagination, one that stretches beyond everyday experience and challenges our deepest intuitions. In the coming decades, new experiments and observations may shed light on these mysteries. Precision measurements of cosmic expansion, dark matter interactions, and high-energy particle collisions may give clues. Advances in quantum gravity and string theory might unify these ideas into a testable framework. Until then, the connection between the dark universe and the multiverse remains one of the greatest open questions in cosmology, a profound mystery at the frontier of human knowledge. As we contemplate these vast possibilities, we are reminded of how little we truly know. The universe is not only stranger than we imagine, it is stranger than we can imagine. And yet, this darkness beckons us forward, inviting exploration, curiosity, and wonder. The universe is an ocean of mystery, vast and deep, with much of its true nature hidden beneath layers of invisibility. Dark matter and dark energy, which together constitute about 95% of the cosmos, are elusive entities that defy direct observation through traditional telescopes. Despite the overwhelming evidence of their gravitational influence shaping galaxies, clusters, and the expansion of space itself, they remain invisible to all forms of electromagnetic radiation. This poses a profound question that has captivated scientists and dreamers alike. Could humanity ever go beyond mere observation and truly visit or interact directly with the dark universe? At first glance, this might sound like science fiction. After all, dark matter does not emit, absorb, or reflect light, and dark energy is a mysterious force causing the expansion of space to accelerate. Neither can be touched, seen, or sampled like ordinary matter. Yet the human story has always been one of turning the impossible into the achievable, whether by inventing telescopes to see farther, particle accelerators to probe smaller scales, or space probes to reach other worlds. So what would it take to break through the cosmic darkness and explore this invisible realm? A search for dark matter particles, catching ghosts in the dark. The leading hypothesis among physicists is that dark matter consists of particles unlike anything found in the standard model of particle physics. These particles, if they exist, would be electrically neutral, massive, and interact extremely weakly with ordinary matter, earning the name weakly interacting massive particles or WIMPs. The challenge is monumental: how to detect particles that hardly ever collide with normal atoms, passing right through planets, stars, and human bodies as if they were ghosts. To rise to this challenge, physicists have constructed some of the most sensitive detectors ever built. These detectors operate deep underground, shielded from cosmic rays and other radiation that would drown out the faint signals from dark matter interactions. For instance, the Lux-Zeppelin detector, located over a mile beneath the Earth's surface in the Sanford Underground Research Facility in South Dakota, uses over 10 tons of ultra-pure liquid xenon. When a dark matter particle collides with a xenon nucleus, it creates a tiny flash of light and a small electric charge that sensitive photomultiplier tubes detect. This technology represents the cutting edge of particle physics and engineering, yet the results so far have been tantalizingly quiet. No confirmed detections of WIMPs. Each null result narrows the range of possible properties these particles can have, pushing scientists to reconsider models or look for different candidates. The challenge of catching these ghost particles weak interactions. Experiments like the Axion dark matter experiment attempt to detect actions converting into microwave photons within powerful magnetic fields, a subtle effect requiring extraordinary experimental sensitivity. The growing variety of dark matter candidates highlights how little we currently understand. It also reveals the vastness of the search, a cosmic detective story with multiple suspects and only elusive clues. The next generation of space telescopes, mapping the invisible on cosmic scales. While particle physicists hunt for dark matter locally, astronomers survey the cosmos to observe the gravitational fingerprints left by this unseen mass. Future and upcoming space telescopes will play a crucial role in this cosmic cartography. The James Webb Space Telescope, launched with the goal of peering into the early universe, will study galaxies so distant their light has taken billions of years to reach us. JWST's infrared capabilities allow it to see through cosmic dust that obscures many objects in visible light, revealing galaxies and structures that trace the dark matter framework. The Euclid Space Telescope, planned by the European Space Agency, will conduct a massive sky survey, mapping the shapes and distances of billions of galaxies to study how dark matter and dark energy influence the growth of cosmic structure. By measuring subtle distortions in galaxy shapes caused by gravitational lensing, Euclid will produce one of the most detailed maps of the dark matter distribution. Similarly, NASA's Nancy Grace Roman Space Telescope will explore dark energy by observing distant supernovae and galaxy clusters with unprecedented resolution and field of view. These telescopes, working in concert with ground-based observatories like the Vera C. Rubin Observatory, will push forward our understanding of the dark universe's large-scale structure and its evolution over cosmic time. Imagining future technologies, from detection to interaction, beyond observation, what would it take to interact directly with dark matter or even visit the dark universe? Current experimental setups can only hope to detect rare, fleeting interactions, but future technologies could vastly improve our sensitivity and open new windows into dark matter physics. Ideas being explored include dark matter colliders capable of producing and analyzing dark matter particles by smashing high-energy particles together, analogous to the Large Hadron Collider, but with new capabilities. Advanced quantum sensors could detect the tiniest disturbances caused by passing dark matter particles, employing techniques from quantum computing and precision measurement. In more speculative realms, some theories suggest the possibility of engineering devices sensitive to hidden forces or dark photons, hypothetical counterparts to regular photons mediating forces within the dark sector. If such interactions exist, harnessing them might allow new forms of communication or even propulsion. Others envision that dark energy, a force responsible for the accelerating expansion of space, could be tapped as an energy source or manipulated through advanced physics yet to be discovered. While this remains science fiction today, history shows that fundamental discoveries often lead to revolutionary technologies. Philosophical and practical considerations. Even if breakthroughs come, interacting with the dark universe will pose profound challenges. Dark matter's feeble interaction with ordinary matter means it streams through us constantly, yet we remain unaware. Engineering probes or vehicles to detect or respond to such particles may require revolutionary materials and sensors. Dark energy, being a property of space itself, cannot be contained or isolated. Its nature as a smooth, pervasive force means that visiting regions dominated by dark energy is fundamentally different from traveling to planets or stars. Moreover, the very nature of the dark universe challenges our definitions of space matter, and interaction. Would exploring it require new senses or entirely new scientific paradigms? The drive to explore the unknown. Humanity's history is defined by exploration, from crossing oceans to probing atomic nuclei. The dark universe represents the next vast frontier, one that will push science, technology, and imagination to their limits. The search for dark matter and dark energy is not just a quest for particles or forces. It is a search for understanding the fundamental nature of reality. Each experiment, each observation brings us closer to revealing the cosmic shadowlands that have shaped our existence. As technology advances, new discoveries will illuminate the darkness, turning the invisible into the known, and perhaps someday, transforming the dark universe from a distant mystery into a place we can explore, understand, and maybe even visit. What if the universe is mostly a shadow? When we gaze up at the night sky, the countless stars, glowing nebulae, and distant galaxies inspire awe and wonder. Yet this dazzling display of light is only a tiny fraction of what truly exists. Modern cosmology reveals a humbling and unsettling reality. The universe as we know it, the world of atoms, photons, and familiar matter, is merely the visible tip of an immense cosmic iceberg. Approximately 95% of the universe is composed of dark matter and dark energy, invisible and largely inscrutable. What does it mean for us that the vast majority of reality is a shadow, a hidden realm beyond direct perception? This realization invites profound reflections, not only scientific, but philosophical and even existential. It challenges our assumptions about reality, knowledge, and humanity's place in the cosmos. First, consider the concept of cosmic humility. For centuries, humanity viewed Earth as the center of all creation, a perspective shattered by the Copernican revolution, showing our planet as just one among many orbiting the Sun. Then, the discovery that our Sun is but one star among billions in the Milky Way, and our galaxy one among billions more, further dethroned humanity's cosmic centrality. Now, the dominance of dark matter and dark energy deepens this humility. The normal matter, the stuff of planets, stars, people, and ourselves, is only about 5% of the universe's content. The rest is a vast, shadowy realm, largely invisible and mysterious. This challenges not only our cosmic importance, but even our ability to fully comprehend reality. From a philosophical standpoint, we must ask, are we limited by our senses and instruments in fundamental ways? Is the universe more complex and layered than we can currently grasp? The shadow universe may be a reminder that our scientific models, while incredibly successful, are still partial approximations of a deeper truth. Moreover, this invisibility raises questions about epistemology, the nature of knowledge. If most of the universe is dark, how can we claim to understand it? We rely on indirect evidence, gravitational effects, cosmic expansion, background radiation, but these clues leave open many interpretation and mystery. Our knowledge is inevitably provisional, evolving as new data and theories emerge. This cosmic shadow also forces us to confront existential questions. If the universe is mostly invisible, what does that say about our experience of reality? Are we living in a world that is only partially accessible? What lies beyond the limits of observation? Could life or phenomena exist within the dark sectors, unknown and undetectable with our current means? Some speculative ideas even suggest the presence of dark life, forms of existence composed of dark matter, or existing in dimensions beyond our senses. While no evidence supports this yet, it illustrates how the shadow universe opens imaginative possibilities about what being means. There are also philosophical implications for science itself. The discovery of dark matter and energy has shown how science advances by confronting the unknown, revising assumptions, and developing new frameworks. But it also reveals the limits of empirical observation. If parts of the universe remain fundamentally unobservable, science must grapple with how to incorporate these aspects, balancing theory, observation, and philosophical reflection. Finally, this humbling cosmic perspective encourages a sense of wonder and curiosity. The unknown beckons us forward, inspiring new generations of scientists, explorers, and thinkers to probe the darkness. It reminds us that the quest for knowledge is never finished, that reality holds infinite surprises. In this way, the universe being mostly a shadow is not a defeat, but an invitation to embrace mystery, to expand our understanding, and to cherish the light of discovery amidst the cosmic night. As our journey through the dark side of the universe draws to a close, we find ourselves standing at the edge of human understanding, gazing into an immense cosmic shadow that challenges everything we thought we knew. The invisible majority of the cosmos, made up of dark matter and dark energy, shapes galaxies, governs the expansion of space, and forms the vast cosmic web on which all visible matter hangs. Yet it remains largely mysterious, eluding our direct observation and testing the limits of our imagination. This exploration reveals a profound truth. The universe is not just the shining stars and glowing galaxies we see, but a vast and intricate dance of unseen forces and hidden realms. The darkness is not emptiness, but a rich and dynamic landscape waiting to be understood. Our journey shows us how far science has come, from discovering these cosmic shadows through subtle clues, to building ever more precise instruments to map and probe them. But it also reminds us how much remains unknown, a frontier as vast and compelling as the stars themselves. In embracing the darkness, we embrace humility. We recognize that our current knowledge is a stepping stone, part of an ongoing quest to uncover the full tapestry of reality. The universe, in its grand complexity, invites us to keep exploring, questioning, and imagining. It pushes us to innovate technologically and philosophically, to broaden the horizons of what is possible. Perhaps most inspiring is the idea that the darkness itself may one day reveal new forms of matter, new dimensions, or even new laws of physics. As history has shown, the greatest scientific breakthroughs often come from confronting the unknown, turning mysteries into understanding. Thanks for watching this video.